Hey there, folks. Welcome back to class. Today should be the last day of August, Monday. And so today, for today's lecture, we're going to talk about a really amazing theory called the theory of plate tectonics. One of the cool things about this theory is it's probably one of the newest theories in science. We've heard of the theory of evolution, the theory of gravity, the theory of climate change, all kinds of theories. But this is probably the newest one. In fact, it didn't kind of consolidate until about the late 1960s and didn't really even become widely known until the 1970s. And so, just as a matter of reference, when I was in high school in the 70s, I learned about this theory and actually did a science fair project on the theory of plate tectonics, and even had some judges who, when they came to judge me, didn't even know, had never heard of the theory of plate tectonics. So this one's kind of near and dear to my heart because it is relatively new, and I've been able to kind of, in my lifetime, sort of see it come to fruition and watch it develop over time. So, getting back again, I want to remind you about theories in science. You know, we've had this discussion before, but I just want to kind of reinforce it. And that is that, remember, in science, theories are incredibly powerful things. They're not guesses. They're not, I've got a theory about something type of thing where I think this or you believe that. They're not things you can believe in. They're not religious things. I believe in this and you believe in that. These theories are based on on literally decades and decades of scientific research, scientific understanding, data, facts. That's what builds a theory. And so, to say that a theory it's just a theory, that's not science. Science, there is no such thing as just a theory in science. By the time you get to theory, it's a pretty well established concept of what's happening. So, with the theory of plate tectonics kind of brought together all the ideas as to how the Earth functions as a system. We knew about volcanoes. We've known about those for hundreds of years, thousands of years. We've known about earthquakes. We've known about all these different parts of geology. But for the first time, this theory brought all that together and explained what causes them, what happens when they occur, all these sorts of things. So we're going to kind of walk through the theory here in detail. And this is a very important chapter because the theory of plate tectonics is going to dictate, it's going to drive everything we understand about the Earth, including weather, including things that happen in the atmosphere, can be driven in part by what happens in plate tectonics. So this is a very important chapter, and you need to really get a handle on it. And again, if there are questions, please bring them up in Grapevine and some of those other areas, and I'll be happy to kind of go over them. There is some stuff I'm going to kind of gloss over. I'm not going to get into huge amounts of detail into some of the stuff, but I am going to give you a pretty comprehensive look at how all this works. And hopefully, again, it makes sense to you. If it doesn't make sense, let me know, because that means I need to explain it a little bit better or maybe go into a little bit more detail. But you really need to understand how this works in order to understand what's happening in the rest of the book, because I'm going to constantly be going back to this theory of plate tectonics to talk about the way rocks are formed, where minerals come from, all that sort of thing. So let's jump into plates then. In your book, it's chapter 4. It's called The Way the World Works, Way the Earth Works, rather, plate tectonics. So let's go through the book here a little bit. In the beginning, they do talk a little bit about this idea of theory and these ideas of, we've heard the word paradigm shift before. So paradigms are the way we think of a particular thing. For example, a paradigm well, let's take the theory of evolution. For a long time, the paradigm was that we didn't fully understand where human beings came from or where animals came from. Um, and so there were different ideas, but a paradigm shift occurs, or what Kuhn calls a scientific revolution occurs when Darwin proposes the concept of natural selection. That in fact organisms change and evolve over time. And so the animals that we see today on the planet uh, are evolutionary species, organisms that don't exist anymore. And so plate tectonics is again one of these paradigm shifts. It began to explain all kinds of things that we had sometimes stupid theories about where they came from. One of my favorites is just mountains. I've always wondered, or people always wondered, if the Earth is as old as it is, if the Earth is old, right? And then where did the mountains, number one, come from, and why are the mountains still here? Because the mountains should have eroded away a long time ago, if there's not some dynamic force that's causing mountains to continue to exist. So plate tectonics help to explain all of this, all these different ideas. So, what do we mean by plate tectonics? Well, let's look at the word. The word plate, obviously, we eat off of plates, right? But a plate, by scientific definition, is something that's kind of flat and spread out, rather thin. Tectonics simply talks about things that are moving or things that are dynamic. So, the plate itself is part of our lithosphere. Sorry, guys, I got interrupted. Apologize. So let's get back to what plate tectonics are. So plate tectonics, when we talk about the plates, we're talking about a part of the Earth called the lithosphere. If you remember, the lithosphere was this solid part of the Earth that you walk around on. It's where we find all of our rocks and all of our things that are solid. So the lithosphere is cooled rock, or frozen rock, actually. Uh, that's what we think of as a rock. Uh, and so the lithosphere are these plates up in the upper part of the mantle. Then just below the lithosphere, if we break it up into big chunks, below the lithosphere is the mantle, but between the mantle, or sort of in between the mantle and the lithosphere, is the asthenosphere. And it's the asthenosphere that the lithosphere actually floats on top of. That's what these plates are going to float on top of. It's described as being plastic, and it's not like plastic when you think of a plastic toy. Plastic as a verb sort of means something that's pliable. You can think of a candle that's been sitting out in the hot sun. It's very different than a candle that's been in the refrigerator or the freezer. So this asthenosphere is somewhat known as the lithospheric mantle. It's this area in between. And when you see these pictures, you're going to see pictures of the mantle and the lithosphere, and they're going to show very sharp lines in between them. Please understand that, in fact, what the line is very blurred there. So there's not a very well-defined line. The whole thing just sort of, as temperatures change, the type of rock and the way the rock behaves begins to change. So plate tectonics says that in fact, the plates that we thought at one time, the lithosphere, the rocks, the continents that we live on, we thought at one time didn't move, but in fact are part of these plates. And you can kind of think of it again as an egg, where the outside of the egg shell, are these plates, pretty thin, and then you have the yolk, or rather the white part of the egg. That is that you could think of as the mantle, and then the yolk part of the egg is sort of the middle. So anyway, go ahead and read this section. It's pretty good. And then when you get down here, you can actually see what these plates look like now. As you can imagine, these plates aren't all the same thickness. The plates at the ocean, the oceanic crust, is quite a bit thinner and actually quite a bit more dense. We're going to learn in a little bit about what the continents are made of, but in fact, the continents are slightly different material. They have oceanic crust under them, but they also are made up of a lighter rock, if there is such a thing, called granite. And we'll look at some granite a little bit later. So the continents actually are these lighter rocks, and because they're lighter, then they tend to float higher on the lithospheric mantle, or the asthenosphere. And because they float higher, then they are above sea level, right? The oceanic crust is more dense and thinner, so it floats lower, and so it's what gets covered by water. We think of in terms of the oceans, and so that's why things kind of look the way they do. Here we can see that, in fact, the continents, or what we think of as a continent, is not just that which is sticking up above the water, but you have a continental shelf, which comes out quite a ways, which is part of the continent. And so continental shelves have this granite, have this lighter material, and then drop off rather steeply into the ocean floor, which has the more dense basaltic oceanic crust. And here they're showing you a little demonstration of what would happen if something's floating. We'll talk about that in just a second. So if we have plates, we must have plate boundaries. And so these plate boundaries are where the plates come together, and they're boundaries because sometimes one plate might be moving in one direction and a plate might be moving in a different direction. And so these are what we call active boundaries or active margins, where plates are moving or rubbing against each other or moving apart from each other, and we'll get into that in more detail. Or we might have passive margins, places where the plates are kind of stuck together. And so we don't have a lot of change in these plates. And we're going to find out, too, that these boundaries can change. Sometimes these plates can get welded together, and the boundaries can sort of disappear, and new boundaries can form. So, again, it's all very dynamic, and we'll see a little bit more of that in a little bit later. So this next section here, here we are talking about buoyancy and talking about Archimedes. Archimedes is the Greek mathematician and early scientist who famously discovered this idea of buoyancy and the fact that a liquid will hold up whatever you put into it, as long as whatever you put into it is less dense than the liquid. In other words, an iceberg floats because the ice is less dense, but it doesn't float right on top of the water. It kind of goes down into the water and will displace the mass of water that's equal to the mass of the iceberg. So, according to Archimedes, what he did was he had a pool or like a bathtub that he had filled all the way up. And he jumped into the bathtub, and of course the water splashes out, right? The water comes out. He learns through math, that what you could do is you could have a bathtub full all the way up, and then as you got in, if you could capture all that water would be the same mass as you. And then there was a very famous story about Archimedes discovering a fake crown. I'll let you look that up on your own. But so the same thing is happening with our continental plates. The less dense plates sink down farther into the asthenosphere, and these are the thicker, more dense oceanic plates. And the lighter ones, which are continents and even thicker, have a tendency to float higher on the asthenosphere, and so that's why we again have land outside of the water, as long as we don't have too much water. If we got too much water, we're all gonna be swimming, aren't we? So how do you identify plate boundaries? I mean, this is talking about the entire world. It should be rather difficult, but in fact, if you remember back in the last chapter, One of the things that we were looking at, although we didn't realize at the time, were these things called seismic belts. In other words, places where there's seismic activity, earthquakes and volcanoes. And so if you make a map, here we see the plates. Here we see the plates kind of exploded, so you can see what the plate shapes actually look like. And remember, the color is the plate, but the little shaded area is what we think of as the continent. So the continent is part of the plate and moves around. The continent moves around with the plate. In other words, this was one of the big problems with Wegener's theory, if you remember. He was talking about the continents moving around on the planet and had a hard time explaining how that might happen. Well, it happens pretty easily, I guess, if the continent is part of a big plate, and that big plate is floating all over the Earth. So that is sort of where his idea of continental drift differs a little bit from plate tectonics. But anyway, here then is another map that shows where these volcanoes and these earthquakes are located. And as you can see, they look very similar to the edges of the plates. And in fact, as these plates move and grind and push past each other, there's quite a bit of seismic activity, earthquakes, and as we're going to find out, also a lot of volcanoes. So this is sort of how we're able to kind of figure out where these edges of plates are over such a large area. All right, so what are these plate boundaries? Are they all the same? No, they are not. There are three very distinct types, and this is kind of important, so you might want to put this in your notes. Let's talk about the three different types of plate boundaries. We have the first, our divergent boundary, and so these boundaries, as you might imagine, are pulling apart from each other. So one plate's going, say, north, the other plate's going south. So they're pulling apart from each other. The second kind of plate boundary we have is called a convergent boundary. So these are plates that are moving into each other. And so here we see an area where one plate is moving and crashing into another plate, and that plate is pushing it down into the mantle, and eventually that plate the material in that plate, the lithospheric material in that plate, the rocks and stuff, will melt and become part of the mantle again. And then we have the third type is called the transform boundary. That's where plates are kind of rubbing against each other. One's kind of rubbing up, kind of if you took your hands and put your hands together and rubbed your hands against each other, that would be a transformed boundary. So let's look at all three of these kind of one by one. Let's start with divergent plate boundaries. And this is seafloor spreading. So many of these divergent plate boundaries are happening, as you can imagine, down in the ocean, in the middle of the ocean in these mid-ocean ridges. So the mid-ocean ridges are these divergent plate boundaries, although we do have a few that are on the Earth, on dry land as it would be, that are divergent plate boundaries. Some of them are very famous. There's one in Africa that's very famous because as it's pulling apart, it's making a large valley down in the ground, and it's a place where archaeologists have found quite a few human remains that are very, very old. There's also a very famous one for you Bible scholars. There's also a very famous one in the Holy Land, right? In fact, the Holy Land is a divergent plate boundary. You remember the Sea of Galilee and the River Jordan that flows out of the Sea of Galilee and flows into a bigger sea called you're right, Dead Sea. And it's the Dead Sea because there's no other rivers flowing out of it. All the water flows into the Dead Sea, and so it's accumulating salt, and it is now so salty there's not much that lives there except for some brine and some microscopic organisms. There's no fish or anything that live in the Dead Sea anymore. And it does that because it's a plate boundary that's pulling apart, and so there's no place for rivers to run out of that sea, and so it is so salty that nothing can live there anymore. But these plate boundaries are moving apart. So I guess the biggest question would be, well, then if they're moving apart, what fills in the gap, right? What happens to the gap? We don't have a hole down to the middle of the Earth. That's correct. So as you can imagine, as these um, as the lithospheric plate is moving apart, it's being replaced by mantle, or rather a lithospheric mantle that's coming up from below and solidifying or freezing. And so that's why we have these volcanoes in the middle of the ocean. Those volcanoes are, in fact, those gaps, those places where that lithospheric mantle is coming up and then freezing and becoming new mantle, new rock. So in a little while, we're going to start talking about rocks and ages of rocks. So if I asked you on a test, where would you find the newest rocks? Well, they would be right here, wouldn't they? They would be here at these divergent plate boundaries, because those are the newest rocks, or anywhere really that you had a volcano where you had lithospheric mantle coming out of the ground and becoming new earth, new rocks, right? So those would be brand new rocks, whereas rocks that we might pick up in the ground here might be several million years old. But here we have some of the newest rocks. So these are boundaries that are pulling apart. Here you can see kind of how that works. And here again is a picture of the mid-ocean ridge. This is the Atlantic ridge, how it's pulling apart. And again, that kind of fits in with Wegener's idea of continents, shapes of continents fitting together. And then here a little bit more detail about what that would do and even what that looks like underneath the ocean. You see these black smokers. This is what's being released there, are the gas, sulfur dioxide, and all kinds of nasty stuff being released into the ocean through this volcanic activity. And here is a map, a very interesting map of rock ages, how old rocks are. And just like we said, that red, the newest rocks, the brand newest rocks, are right around these mid-ocean ridges and places where rock is being formed. Whereas the oldest rocks then would be farther away, with some of the oldest rocks being near the next group of edges that we're going to talk about, where we look at subduction. So convergent plate boundaries and subduction. Convergent plate can't talk. Convergent plate boundaries are where plates are coming together, so they're crashing together. And these are where plates are converging, coming together. And usually what happens, or a lot of times what happens, is when these two plates come together, one plate will be more dense than another plate. And the more dense plate will have a tendency to kind of slide under the less dense plate. So something lighter would have a tendency to kind of roll up on top of something that was heavier as they were moving together. And so since the oceanic plate is this more dense material, usually what happens is the oceanic plate will roll underneath a continental plate, causing what we call subduction. And then here we can see that happening and see what that might look like. A good example is in the Pacific, near where the plate ends near Japan. There you can see the island of Japan. There you can see these different island arcs. We'll talk about them in a little bit more detail. But those are places where the Pacific plate is moving and moving underneath the Asian plate and causing earthquakes. They cause these very deep trenches. As a matter of fact, the deepest place in the ocean is just right there off the southern part of Japan, in the Marianas Islands. Almost 7 miles deep is the ocean right there at that trench. Plus, they cause earthquakes and volcanoes. So Japan has Mount Fuji, the giant volcano near Tokyo, and Japan, as a set of islands, is in fact all volcanic, very similar to Hawaii and most of the islands in that area. So these are the convergent boundaries. They do create these arcs sometimes. Probably one that we think of in the United States is up near Alaska. The Aleutian Islands in Alaska are, again, one of these volcanic arcs, and is a place up north where these divergent or convergent boundaries are causing these trenches and volcanoes and earthquakes. The third one is a transform plate boundary. these are where plates rub against each other. Again, like I said, if you put your hands together and kind of rub them together, that's kind of the way these plate boundaries would work. Probably the most famous, or the one you're familiar with, is the one in California, right? The San Andreas Fault is a place in California where the North American plate is rubbing against the Pacific plate, and taking part of California eventually in 100,000 years or so will be out in the ocean, be the California island, I guess. But these plates rub together, rub against each other, and they don't do it very smoothly. So again, if you took your hands and tried to move them, put a little pressure on your hands as you put them together, and try to move them slowly, you can't do it. They kind of have a tendency to jerk, don't they? And so that jerking motion is essentially an earthquake, is what happens in an earthquake. The plates kind of get locked together until enough force is generated, and then they sort of move with a big jerk. And that big jerk is what we're going to learn, I think, in Chapter 9 about earthquakes. And so these are the transform boundaries, and there's quite a few of them around. We don't see a lot of volcanoes with these, but we do see some of the bigger earthquakes. Special locations, triple junctions, don't read too much about those, but hotspots are pretty cool, because one of the more famous hotspots is Hawaii. And Hawaii, if you look at the plates, you see the volcanoes in Hawaii, they're out in the middle of a plate. They shouldn't be there. And so these are hotspot volcanoes, places where the lithosphere is thin, and that lithospheric mantle has made its way up and created islands. Another famous one is Yosemite National Park, or excuse me, Yellowstone National Park. Yellowstone is actually a super volcano, and is in the middle of a hotspot because it's in the middle of a plate as well, and shouldn't really be there. But it is there because of just some thinning, and the heat from the mantle is able to get up and cause all kinds of geysers and smoking mud pots and all kinds of cool stuff. So there's a picture of some of these hotspots there. You can see Yellowstone in the middle of the United States, and you can see Hawaii over there in the middle of the Pacific Ocean. And then there's quite a few of them, a whole bunch of them. So hotspots are not rare, but they're sort of out of the ordinary. So how do these boundaries form? How do they die? Well, a boundary can form simply when an area of lithospheric mantle gets very, very hot and begins to melt, and therefore it heats up and breaks apart the lithospheric crust above it, and then will cause a plate to start moving. This usually happens underneath the ocean. That's why we have these mid-Atlantic ridges in the ocean, because that's where the plate is the thinnest and where it would probably take place. However, it does happen in continents, and probably, if you remember, Dr. Wegener, was talking about all the continents were one big continent at one time and got broken up, and that's probably what did it, were these hot spots in the middle of a very thick continent that had a tendency to break it apart. This is called continental rifting, and again, we don't see that much these days, but probably back in dinosaur days, it was a pretty big deal and pretty dramatic. We've seen a little bit of that happen in places like Iceland. We see some of these continental rifts take place. Iceland, by the way, is right on top of that mid-ocean ridge, the Atlantic Ridge. And so you can go to Iceland and actually be on the mid-Atlantic Ridge on dry land. So that's kind of a weird place to be. But anyway, there are some of these hot spots. And let's talk just real quick. The last thing we're going to talk about, I know this one's kind of going on a little bit long, but let's talk about why this happens. In other words, what's the engine? What makes the plates move? If you remember, that was the big problem that Wegener had. He couldn't explain how these things moved. What caused the continents to move? And so what we know now is that the forces acting on these plates, well, there's several of them actually, but the main one is called convection. And convection is simply where we have a hot area In that hot area, the material under it or in that hot area tends to get less dense and it rises. As it rises, it gets farther away from the hot spot. Therefore, it starts to cool. As it cools, it gets heavier and it falls back down, and the whole thing starts over and over again. It's kind of like if you've ever boiled rice or seen something boiling in a pot. You see that kind of rolling boil. Well, it's rolling because the flame of the stove or the heating element of the stove is heating up the pan, which is heating up in one specific area. So it heats up the water there, and that water gets less dense. The molecules move farther apart. It gets less dense and rises. And then as it rises, now it's away from that hot spot and up near the air. It's going to cool. As it cools, it moves away from that hot spot and sinks. And then you sort of get this rolling thing happening, this convection happening. There's also ridge push and pull. Ridge versus push is pretty simple. It's like if I took a big dollop of honey, put it in the middle of a plate, the dollop in the middle is up high. Gravity's going to kind of push it away. So the whole thing's going to kind of spread out. That's kind of what they're talking about there. And then finally, the slab pull, as the plate is sliding underneath in a subduction situation, as the plate is sliding underneath the mantle and going into the mantle, it's literally being pulled. So it's almost like if you took a towel and started pulling on it on one end, the whole towel would start moving. Finally, speed. How fast is this all happening? Well, different plates move at different velocities, but the average is about 2 centimeters a year, or 2.5 centimeters a year, which is not very fast. It's about as fast as your fingernails grow. So that's how fast we are moving away from Europe. In your lifetime, the continents will move about 6 feet apart. so the movement is very slow. But and that's probably why we didn't see it, right? I mean, if something happens that slow in geologic terms, in geologic time, it goes pretty fast, but in human time, it goes pretty slow. Again, at the end of this chapter are those big diagrams. Those things are really great for helping you see how this all fits together. And again, these are good, so make sure you take a look at those and show you how this all fits together. And make notes, make little drawings. I will ask you maybe to draw some pictures on the test. So keep these in mind when you're trying to put all that together. All right, there are the plates. There's all the different directions they're going, so you can see where one plate kind of runs into the other one. There you can see up here, you can see California, the plate's moving off in this direction, and then the American plate is moving in this direction. So that's where we get those earthquakes. Alrighty, that's the end of this chapter for the most part. There are those chapter questions, review questions. Pick 5 of those if you're going to do this chapter and turn those in to me. And I will see you on Wednesday.